Welcome back. This is an Aleks training video on applying like dissolves like. So as we've seen in class, if you have salt, it'll dissolve in water. And the reason why is because water is polar. One side of the molecule of water is positive, the other side is negative. So it surrounds the positive ions and yanks them apart, surrounds the negative ions and yanks them apart. So it's the polar quality of water that makes it solvent. If you were to put something that's not polar in water, it would not dissociate, it would not completely break apart. Likewise, if you were to put table salt in fingernail polish remover, it would simply fall to the bottom of the jar. It wouldn't dissolve. It's not the wetness that dissolves the salt. It's the polar quality of the water that rips the salt apart. So you're going to see that if you want something that's nonpolar, you want to put it in a solvent that's nonpolar. So something like wax or grease that is nonpolar, you would want something like gasoline to wipe it off. So if you're using paint that is not water soluble, you would need some kind of a paint thinner in order to get it off your hands. Water wouldn't do it because water doesn't dissolve a nonpolar molecule like paint. Okay, so that being said, that's the underlying thing. The hard part of this assignment is knowing what's polar and not. Okay, we've done it in the past, but it takes lots and lots of practice to see it. And then being able to see when you look at these solvents, are they polar, are they nonpolar, and what is it in the solute that you need. All right, so rather than teach it, I'm simply going to go through these problems, and I'm going to answer every single possibility. And what about this possibility? What about this possibility? This may take you a few times before you can pass this one. All right, let's look at the left of this first one. This is calcium chloride. Calcium's on the left side of the periodic table, chlorine's on the right. That makes it ionic. That means that these are ions, and ions are broken apart by polar molecules. Polar molecules, we want something where there's one side positive, the other side negative. All right, carbon tetrachloride at the top. Carbon and chlorine are a polar bond, but all of these four are simply going to be symmetrical. So it's going to look like a jack, like when you played jacks. You're going to have a tetrahedral shape, and every one of those chlorines are being pulling on the carbon unevenly, but they're all around the center carbon symmetrically. So it's not polar. The alcohol is polar. Okay, you're going to have the oxygen has a higher electronegativity than the carbon, so it's going to pull more, and so the right side of that alcohol is going to be negative, the left side is going to be positive. For that reason, a polar molecule like alcohol is going to dissolve that salt. So I would pick alcohol, and I would not pick carbon tetrachloride. All right, the next one is a little scary. You don't even know what these are. These all have names. Don't even worry about their names. But look at what they're made up of. Okay. Now, instantly, if you have no idea about it, you would say like applies like. Oh, well, this looks like this, so it must be the answer. Not necessarily. Just because it looks like it doesn't mean that it's like it in many ways. What do you see? Okay. First of all, I see polar. I see that oxygen has a higher electronegativity than carbon. Nitrogen has a higher electronegativity than carbon. So you're going to have negatives here and a positive side. So this is a polar molecule. Well, so is this. This has a negative side and a positive side. The water, this has a negative side and a positive side. So both of these are polar. One is going to be better than the other, though, because I can notice and see that this is NH2, and NH is one of my hydrogen bonding things. Remember, hydrogen bonding is with nitrogen hydrogen, oxygen hydrogen, and fluorine hydrogen. So this means that this also is not just polar, but it exhibits hydrogen bonding. So even though both of these are polar, water has hydrogen bonding. Remember, you have oxygen, hydrogen here, and it's going to dissolve it better. Okay, for that reason, I would pick water as my solvent. Okay. All right, so let's keep going. What about this huge monster? Okay. Well, again, the picture here, this dimethyl chloride looks very similar, or sulfide looks very similar to this. You would think, well, this is like this, but what is going on here? Okay, I've got, it's polar, okay, because this is pulling faster. I've got oxygens pulling. I've got oxygen, so I've got negative this side, negative this side, negative this side, negative this side, positive the rest. So it's sided, so it's polar. Well, so are these. This is oxygen, hydrogen, so it's going to pull harder than the carbons will, so it's negative on this side. This is the same. They're both polar. Okay, so they would both dissolve in polar, both of them would work as a dissolvent. Which works better? Okay, well, it's very similar to the one we did up here. Here's OH. OH. This is, remember, OH, NH, and FH are hydrogen bonding. So if you can, of these two polar molecules, pick one that also has hydrogen bonding, okay, this ethanol, then it would be better. So it would be better. So even though that they're asking for like dissolves like, and this one looks like this, and this one looks like this, doesn't necessarily mean that it's going to be the best. Now, if this were the only polar molecule and this were nonpolar, then this would be like. Okay, likewise here. I'd say it's tricky. It's not tricky for this lesson. It's tricky for past lessons that you may never have learned properly or learned fully. So just practice and we'll work at it in class.